Swayam Prabha. Digital India. Educated India.
Good morning, welcome you all to the next lecture in this particular course on analytical spectral microscopy applications of inorganic compounds and nanomaterials. In the past few classes, a couple of classes I've been talking on the thermal methods of analysis, and in the immediately previous class I talked to you about the method on differential scanning calorimetry, and then started looking at some examples of various types. And lately we were looking at some examples particularly of the organic in nature or polymers in nature. So let's continue with a number of applications in this particular class, so that whatever we learn from these thermal methods would become very applicable, and then can understand everything in order to identify as well as quantify the compounds. So look at this particular example that I have on this slide here. This is a mixture where the lignin and cellulose, these kind of polymer mixtures, you can see there is one, the thermogrametric drop in the weight, and there is another thermogrametric drop in the weight. So this comes at this particular temperature, this will come at this. So this is around 300, this is around 400, close to that. So therefore you are able to differentiate both of them, as you can see here. So you can differentiate definitely. This particular thing is the differential thermogram, which is just a mathematical function, the dw by dt or dm by dt. So you can quantify. Now by looking at the area of this car under this particular peak and this, by deconvoluting, you can tell the ratio also present in that. Also in the previous class I talked to you a few the polymers, and you can see PTFE, PFA, PTFE, all these things. So the glass transition, and these are the melting temperatures. The melting temperatures of PFA and PTFE, they all differ. So therefore you can definitely use this technique quite well to quantify, to also detect. So what all things one can get? You can get the glass transition of the polymers, the plasticizer loss in some cases, and in some cases residual curing, but not necessarily all, crystallization in some cases, melting in most of the cases, oxidation or degradation in many cases, either the oxidation or degradation or both, these kinds of things. So you can see. So from the polymer point of view, you can quantify all of these using the DSA. You can also find at what temperature each of these processes occur, and those parameters become the characteristic for you to differentiate one polymer from the other. Here for one example is shown for the PET polymer, the glass transition and the crystallinity, and then you have the melting. Okay, so you can see that. So not necessarily all of these 6, 7 can be seen in every case. So whatever you can see, 2 or 3 parameters are good enough to compare with another polymer, or when you have a mixture. So because one makes the blends of the polymers for application purposes. So you can look at other example. This is a coal. You have a lot of organic, you also have some kind of an inorganic as well in that. Look at the thermogram. So you can see there is a very small decrease in the weight. This is the percent, this is starting from 100. And this particular thing goes up to about 40, 45 or so, or 50. So and then the first major weight loss is around 19%, and this is labeled as peak 2, this is labeled as peak 1, and the next weight loss is very sharp, not much broad. Here this is very broad, slowly things are happening. Here very fast the things is happening, and that is peak 3, which is around 35%, and this is the peak 4 where you have the 44. So here it is given the time. So how can you have a time? I already explained to you several times, You can also use the x-axis time, because you are going to use the rate of the temperature variation, and multiply by time will become the temperature. So, temperature at any given point is the rate and multiply by the time. So, that will give the temperature. So, you can use the rate, you can use the time, you can use the temperature on the x-axis of that. Okay. So, the first one is just a moisture which is adsorbed kind of thing, very little. Then comes is all kinds of volatiles, they are going up within this. I will show you temperatures from this little later on. Right now you look at this one, and the third one is the carbon. Whatever the carbon present in that gets burned depending upon what atmosphere you are doing, and this must be probably used in the air or thing. So, then this will get burned, and then you have the ash. So, you have in this whatever is the ash left over, will come to that too. So, you have the percent of volatile organic ones, carbon itself, and the ash, which is basically inorganic based ones, oxides, hydroxides, those kind of things of metal based ones. So, this is nothing but your differential thermogram into these ones. So, you do not need to look at that. From another source I picked up where you can gauge the temperatures as well. Okay. So, this is your thermogram, and not much change with 0.9% only with the water. Then volatiles coming up here. In this sample 23.5, in this sample 19.25. So, from sample to sample it will obviously differ, and this particular thing is carbon getting here 67%, here 35%. And suppose if you use up to here and is used under nitrogen, you can make that one. Use beyond that oxygen if you use, and the remaining thing can get burned. So, that is all the carbon can burn in oxygen and go as a CO2. So, that will be, and you can use back the nitrogen. So, from this temperature to this room temperature to this, nitrogen is used. From here to here it is oxygen is used. Again from here beyond, nitrogen is used. You can see all the cycles. So, you have seen the thermogrametric analysis curve, because after this if you use nitrogen nothing will happen, but if you use oxygen something may happen. So, here initially temperature 110 up to that, and up to 950 this whole thing will happen, and so beyond that again you have the cycling this. So, under the nitrogen. Okay. So, you can use different conditions also in the same experiment. As you have seen here, up to here nitrogen used, beyond that oxygen is used, and beyond this temperature again nitrogen is used. So, these are all to probe how these samples, what is there in the sample, organic type, inorganic type, easily burn, does not easily burn, do they burn and go as a gaseous, or do they not. And if you want, you can attach the whatever the products coming out into mass spectrometry and analyze, which I have already explained to you earlier. Okay, here is an example of put a polymer into a carbon black. So, that means you make a composite. So, the carbon composite or graphene composite or graphite composite, those kind of things. Composites are that, with the polyethylene is a polymer. So, here you can see this there is a 75% of the polyethylene, nitrogen nothing will happen because that is degradation of that. Then if you use oxygen, this will start burning down in this. So, heating rates, etc. So, you can use these techniques, combination of the techniques of TGA, DSE or DTA, all of these kind of things together for referred as the thermal analysis, to find all these samples of organic based, organic, inorganic based, composite based, all of those. Okay, let us look at some real lifetime kind of applications. So, here you have seen the doors where there is a paint and the top layer which is a white layer, white door polymer. So, you take a peel out a small piece of that and make into a small powder type and put into this machine or the TGA. This is obviously a composite. Now, look at the thermogram of this. So, what is happening? So, what is happening here is up to 400. So, there is a loss starting from 250 to up to about 350, 400. There is a first loss, and that is because you have the polyester present in that, because a polymer mix that they use. So, one is polyester, styrene, fiberglass, all of these are polymers. So, these all the polymers were made into a blend. I have been talking to you blends earlier, and that you can call as a composite. And this whole thing is put into calcium carbonate, and that is what is made as a top layer on your doors. and small top layer on the doors which comes as a white material. Then you can put your paint on that, not a problem. So the first part goes with this, the next part goes between the 400 and 500 degrees Celsius, that is styrene. How do we know? Because we know their pure the decomposition temperatures, we already know separately, so that from that we can make out. And how much is there from this area? How much is going from 100 to about 80, that is 20% difference. From here to here 10% difference. So from that you can make out what is the ratio of the polyester with respect to styrene with respect to fiberglass. The fiberglass starts decomposing only beyond 600, 650 and then goes up to 750, 800, and so you can get. So all these blend. Now the strength of your material depends upon how much it is. So now if you have your own startup company, then you can start playing with each one of these in terms of their strength, in terms of the financial thing, in terms of making a composite and composite strengths, etc. Those are all can be worked out, and that is how people make new versions of the same for increasing the durability, because you put on the door top, obviously this is exposed to sun, it is exposed to rain, it is exposed to moisture, it is exposed to air, everything is there. So therefore durability you look at. So the durabilities will depend upon the composition. So therefore you can, if you are a smart enough guy, you can play with these composites, compositions, and then come out with a composite which is more durability of all that. At the end you have a calcium carbonate, and you have already studied the calcium carbonate. That decomposition also you can study later on. So instead of calcium carbonate you can use something else, you can use something else. So all these kinds of things. So you can start making huge amount of composite materials which will help building composite materials for these doors and other application purpose. Okay, there is another composite shown on the right side here, the PET polymer with the graphite. Okay, so different extents. So you take a pure PET, you take PET with 2% of graphite, 5% of graphite, 10%, 15%. You see that thermograms. So this the green one is here, that means its weight loss is less. This pure one is below, and this red one 10% is here. So like that. So you have all. So as you increase the percent of the graphite that you have mixed with this and formed a composite, the thermal loss is less. In other words, it will be lost at the higher temperature. That means thermostability. So your polymer is PET, but you are adding some graphites into that to make it stronger, to make it heat resistant or heat less amenable for heat. So therefore heat stability. So this is another application where you can use. Okay, you've seen the tires which we use for all our automobiles and for everything, etc. So if you look at that and heat that, take a small piece of that and heat, it started with 100%, it will go up to almost close to the 5% something 0. So what are all the materials? There is one major drop, another very major drop of the weight, and then another. So 3 very major weight losses are seen, and the first loss is in this example case, not everywhere. 28% of the oil is used, and the polymer is 43.9% of the polymer is used, and then carbon black which is used 32%, and then there is some inert fillers are there, and these are the inert fillers. So now you can play with all these, and then you can make a tire which is more durable depending upon the roads. Okay, so certain roads you have easily worn out, easily breaking, etc. Certain places cool temperature, low temperature places, you need a different kind of tires. So you can play with these compositions and then make the kind of a tire you require, whether you would like to use in a rough roads, in high temperature roads, or the low temperature roads, in the snowy roads and the snow, all these kinds of things, when it's raining, etc. So this thermogrammetric analysis will help you a lot in this. So don't take these values as a standard values for all tires, it will change. So that's how you can make. So it has an oil, and what kind of oil, that also you can look at that, and whether you can change the oil percentage or change the oil itself in a different one, polymer percentage, different polymer, carbon black, variety kinds of carbon blacks can come from by burning a lot of organic material, wood materials, etc. You can try to change. So every one of these is a replaceable one, So if you are a startup company guy, you can play with all these details and then make a product which is cheaper, which is more durable kind of things. Okay, we eat bread every day, and if you look at this, the quality of the bread can also be talked in terms of their water content, in terms of their degradable organic material, etc. And if you look at the bread, you have the surrounding, the crust you have, and then you have a softer material of that. So you look at the crust material of the bread, and this is the weight loss, very little here slowly and then very slowly going. So over a period, over a temperature range of 50 to 200 plus, so very slowly going. And then there is another major drop between 250 and 300, and that is how it. So if you look at the interior portion of your bread, what you are taking, so you can see that the weight loss is happening much more faster than this and more amount of that. Okay, and then another major drop. So essentially, now if you take the dm by dt or dw by dt, you will find one very broad peak for the crust part of it of your bread, and then another one which is very close to both the things. So from this you can easily make out the difference, kind of a material, the water loss that you have in the crust part of it and in the interior part of it, because they use a slightly different combination to make the crust, and then their heating portion will differ, and that will decide the crispness and the holding the bread, etc. So the bread makers will worry about obviously those things. So you can, if you see that the interior part of that loaf of the bread, so you have two major peaks, one around 110, another around 150, etc. Whereas this is around 70 to 80 degrees Celsius. Here they are more or less the same kind of a weight loss that you have. So based on this, you can talk in terms of the quality of the bread that you have as well. So parameters have to be combined with that. So whenever some quality check officer goes there, obviously they will do some thermal analysis and then compare with the standard one and see how it is deviating. So occasionally the samples have to be checked, etc. And even the company people will also keep checking after every making the stages. So they will look at those the qualities also can be used for. There are some thermoplastics are of course are of great use, but if you can make some thermoplastics where you can easily degrade those thermoplastics, that is nothing equivalent to that, because nowadays most of the problems of environmental problems are coming from the plastic waste. So that is not getting degraded. So that is where the problem is coming. That's coming into the recycling back into our environment in terms of air, in terms of land, in terms of water, in terms of food. Everywhere comes back to us, and that is that really kills all the organisms in water which are growing. So therefore the environmental remediation is an important aspect. So for that people are always looking for alternates. So this is one of the alternates. If you can make the plastics using some proteins, the proteins are derived from the plants, so therefore no problem, and they can be easily degraded back. So that's where thing is. So in that you look at the properties of that by using the TGA. These are the legumes, is kind of a lentils, beans, these kind of things where you can extract, or chickpeas, these are the ones where you can extract the proteins called the legume proteins. These proteins later on are used at certain the purity level. They can give a good thermoplastics, and below that purity level the thermoplastic properties will not be good, so therefore they will not be used. So that is what is being identified by these experiments. So you have isolated these legume proteins from these different sources. So each one is one different source. The beans, chickpeas, faba beans, lentils, peas, variety of these things, and the right side number tells you 75% purity, 70% purity, 88% purity, 75%, 77%, etc. These purities, how do we know? Or yes, you can know from there the degradation temperatures. So dW by dt or dm by dt will also tell you, and you can look at those aspects of it, and that is where it helps you what purity of these things are there. So these are some more beans at 55 the percent of purity, 45% of purity, 50% of. So they have looked at making the plastics using the ones which are above 60-70%. They are below 50-60%. They found that the plastics that come out are much better when you have the purity is around 65 or 70 or above of the purity as compared to those which are below 60% of the purity. So, who is talking about this purity? Yes, your thermogravimetric analysis. So, thermal analysis as a whole. You can combine these with DSC, you can combine with the DTA, all of those things can also be combined with that too. So, that is the advantage using the thermal analysis to see the purity of the protein materials which you are using for the purpose of making the thermoplastics. So, these are all degradable, they can be denaturated without degrading and thus they can be extruded out. So, that is where you are going to use the proteins, because at the end of the use of the thermoplastic, the plastic has to be degraded. That is what is much easier with it. So, there is no pollution or hazardous things that you are adding. So, you have the leather purses, leather bags, etc., etc. So, you want to know how old it is. How do we know how old it is? Just by looking at it? No. So, by looking at its thermal analysis. One of the examples shown here is a differential scanning calorimetry. How it is possible? It is possible because that leather has the fibrils. The fibrils are made up of the collagen. So, you might have heard collagen is a protein which is a structural protein, we know, and the structural proteins, they make the structures of this. So, the collagen, how well the collagen, the bundle is still stable, how loosened it is, destabilized it is. From that you can make out how old is the leather. So, that is the principle with that. So, if it is loose, your DSC value will be different. If it is very tight, your DSC value is different. This going out can happen because your fibers are your leather fibers, or leather is continuously exposed to air, moisture, water, other things, etc., and some materials that fall in. They all can make some kind of a chemical modification on your interior fibers that you have. As a result of that, slowly there can be the change in the fibril strengths. So, the fibril together, and that is what will change in your DSC thermogram. You can see here. So, this is for one of the example of that. You can see the chemically unmodified collagen comes at here. If it is chemically modified collagen, it will come over there. It can come even here. That is 54 degrees Celsius, 70 degree, 80 degree, etc. And then gelatinized collagen, if it is the collagen is gelatinized. So, this whole the DSC is based on the collagen that you have in your leather. You take a small piece of that one and then you study all these as a function of temperature. So, room temperature up to about 100 degrees Celsius. So, you can make by deconvoluting this area, you can make out that. So, from that you can tell that how old. So, by making some kind of a comparative catalog. So, you will have a standardization. Right now I do not have the standardization here to get exactly the how old it is. Of course, with approximate in terms of years, etc., in terms of days, those kind of things can be identified by going through a catalog of standardization catalog, if you can make that. So, but basic science behind it is studying their DSC on that. Okay. Their twist strength will differ depending upon whether the fiber is exposed, fiber is the chemically modified, all those kind of things. Okay, you can also make some kind of a commercial materials which are used for absorbing materials, etc., because you use in your kitchen on your table to clean, etc., when there is a water. So, they will be absorbing. So, these are made from materials like the ones which is chitosan is one polymer, again a natural polymer, EDTA, urea, used in different ratios and make, and each one of that has its own thermogram. Here you can see that this is it. By taking this together and blend it, then you get this one, CHEDUR, and you can study its thermogram, you can study its dW by dt, so you can see the temperature. So, this is coming with that kind of a strength. So, you can change the ratio of raw chitosan, EDTA, urea. What is happening is that when you blend them together, formed through the cross linking of the chitosan CH with the EDTA urea, and that is what it forms this compound. So, depending upon the extent to which you have used each of that, their cross linking and the pores that are formed, your water absorbing ability will change. So, you are a manufacturer, so you can use these parameters on that. And if somebody wants to look at the quality control of that, they will again look back into the thermal analysis and work out that too. Okay, so thermal analysis, some examples for even for clays. So the clay here can structures as you keep heating. So these are heated at a very high temperatures. The previous case, the leather, where you look at low temperatures up to 100, because you don't need to go higher. So these water absorbing materials, is a higher temperatures they are made. At that higher temperatures you mix all of them and then made. These are clays at different temperatures, going from room temperature up to 1000, 1100, 1200. What will happen? The clays are what? Clays are basically aluminum silicates with a lot of water, a few other organic stuff attached, etc., etc. in that. They will have different kinds of structures when you keep heating, because to different extents of water loss, different extents of the cross linking of the oxo bridge between those things. So they will change the structures. So in this particular example, this is the TGA curve. The first small thing in the red circle, this happening around 70 to 100 degrees Celsius. This peak is because of the physically absorbed water. Okay, and then the exothermic peak here is here starting from 450 to about 600, around 560. This is transformation of the kaolin, is one kind of a structure, to the metakaolin. Okay, and this is because of dehydroxylation of that. So there's a lot of hydroxyl groups are there, and the dehydroxylation, and then some kind of a O bridging between these things. So, and there's another peak which is happening beyond that, around 1000 degree or this. So this is converting from metakaolin to a spinel kind of a structure. So these are what structural change. So as a result of that, what will happen? Your clay strength will change, your clay look will change, exterior, all these kinds of things. Your clay bending properties will change. So their elasticity properties will change, structural strength will change, they look on that. So therefore you can make, you cannot make, etc., etc., brittle. So if you look at that, these are the DTA curves, heat flow DSA curves. You can see exothermic, endothermic peaks that are coming over here. So this is endothermic, another endothermic, small exothermic, and kind of things that also is there. So nothing. This also explains the same structures of kaolinite to metakaolinite to spinel structures. So these are the kinds of changes that are occurring. As a result of that, your properties will change. So how you can utilize. Another example is shown for characterizing that. This is your TGA thermogram here, and different regions are labeled here. Is labeled as this one as a W, and W plus ZW1, ZW2, and BSW, etc. You see here. So that is interparticle water, that is just adsorbed kind of thing. ZW1 is a part of the zeolite water, and ZW2 is the towards the end whatever is losing, and DSBW is dehydroxylation, pectatite, and dehydration of the bound water, palgyroskite, etc. Different types of structures they are, nothing but dehydroxylation of this one. So at different levels, as I mentioned earlier in the previous slide, based on that, so that is all going at different temperatures. So you can see something below 100, around 240, around 520, around 826, around 860, 980, etc., etc. So the structural change as a result of all these things is happening. So that is how you can characterize. So if you take another kind of a clay, these values will change, the amount of each of these will also change, because these are all not single compounds, they are a mixture or they are composite kind of things. So the thermal analysis can also be extended to various textile materials. Suppose you have a simple polyester, have this rubber, this, you have a silk material, this kind of thing, and you have a cotton material. So using these as the standard peaks for those kind of things, as a polyester or a rubber or a silk or a cotton, then you take your material and you can test that one. So different in the textile industry. Even medical industry also one can use. You have a tip, the needle end, if you take that, if it is used once, you can easily make out something is coming on the top. If it is not used, it is a cleaned one, you can differentiate that. So by using the DSC thermogram, if there is something very strongly absorbing, there is some organic matrix is still there on the tip, so you can make out the used one or unused one. So, a variety of these kind of examples are there, and so we can use in applications. So, all of these are for making composites. So, composites, many of these could be nanomaterials as well. So, we have seen a lot of examples. In fact, many of these things are useful if somebody is planning to manufacture these things on their own with some knowledge that is being. So, what I would like to extend this is to you, please do some kind of a home practice. So, extended practice, knowledge enhancement, you can enhance that one. And if you are a person who are looking forward to having your own industry build or your own startup, so you can use these ideas into that. So, thermal analysis. So, everywhere it is used, nanomaterials, textile materials, biological tissues, glass materials, petroleum, biopolymers, paint, food, pharmaceutical, cement, composite, electronic, soil, plastic materials, polymer, other medical materials, metallic constructions, cosmetics. So, even construction materials also, cement you have seen, composites, energy materials, many more. So, there is nothing that you can devote. So, all of these are routinely useful, and one can do get into the commercial with some knowledge, because today most of the business is based on the knowledge based business. So, therefore, the knowledge is important. Here is just based on the thermal analysis techniques. These instruments are very simple, easy to get. You do not even need to buy for you. If you are starting your own startup, you can easily get these samples done by the other analytical labs, who will charge you very little kind of money. So, therefore, that is highly useful in looking forward for even building some startups and then industrial kind of things to produce materials at a higher or cheaper rate and with a higher durabilities, etc. We will still continue to look at, in the next class we will look at one another technique which I have not been able to cover so far, is the isothermal titration calorimetry, and then we will also look at some few problems of that. So, these things we will look at in the next class. Thank you very much.